Good afternoon. My name is Matthias Niemeyer, and today I have the honor of introducing my dear and highly esteemed colleague, Professor Dr. John Kennedy. Now, rumor has it that the city of Toronto is considering renaming one of its major streets from Kennedy Road, after the family of Ontario's former premier, into Kennedy Road, after John M. Kennedy, my colleague. Now, this might be a rumor that is yet to be confirmed, but even if it turned out not to be true, I think the proposal should be made, and I'm taking the opportunity here to convince you why. Dr. Kennedy, John, is a researcher in perception, worldwide renowned, and as such he asks questions no smaller than what is reality and how can the human mind know about it. With this, Dr. Kennedy represents in the best possible sense the discipline of perception, its splendid past and its bright presence in the future, through consensus and dispute. Let's begin with the past. Dr. Kennedy has strong roots in the traditions of the discipline. His doctoral supervisor was the influential J.J. Gibson. Gibson was preceded at Cornell University by Edward B. Titchener, who was one of Emeritus' first psychologists in the first place. He himself, Titchener, was a student of Wilhelm Wundt, who was known as one of the founders of psychology in general. And Wundt himself was a student of Hermann Helmholtz. So we have this long lineage. Strong roots that are here with John. Now, John isn't just roots, but it's a blossom tree. So let's talk about the present and the future. What could be more contemporary than the YouTube video that features Dr. Kennedy's work with a blind Turkish artist? This video has passed the millionth hit, I think, the year before this one, or 2010 even. It's highly popular. John Kennedy is an internet star. What could be more contemporary than Dr. Kennedy's invited addresses at exhibitions, just to mention Manifesto number 8, which is the European Biennale of Contemporary Art. Further distinctions and awards. I couldn't just mention all of them, it's impossible, but just a few include Dr. Kennedy's induction as a Fellow of the Royal Society of Canada. That was in 2005. And in 2009, he assumed the distinguished rank of University Professor of the University of Toronto. So it's a very rare honor that he received there. He was a visiting fellow across the world, from Austria to Australia. And since 2010, he is a Professor Emeritus, so that he can travel even more. And so just this year, he has to follow invitations. He just has to follow invitations to London, Paris, Mainz, and New York. Dr. Kennedy has about 200 publications, everything included, several books included as well, in which he reports his research on vision and touch, picture perception, metaphors, and contours. And so to learn more about this research, please join me in welcoming Professor Dr. Kennedy.
Thanks, Matthias. Very nice invitation. When Matthias mentions all the nice things that have come my way over the years, luckily, I'm reminded of a guy that I saw when I was getting my fellowship with the Royal Society. And there was one guy got up and he had a lapel badge or two, and then they listed all of the fellowships and honors that he had. So I talked to him afterwards and I said, you know, I see you've got 2 badges, but you know, you could have quite a few, obviously, from all the things that were said about you. And he said, yes, but I don't want to look like an unemployed Russian general. So I must thank a lot of people for asking me here. I'm going to talk about the basis of perception. In order to do that, I'm going to focus on a particular question, which is, what is a picture in vision? And then I will add in touch. My answer will have three parts. Cave art outline. Outline is the first part. Renaissance perspective. Perspective is the second part. And modern metaphors. Let's see, how do I get this to advance? Okay, there we go. So thank you for the invitation to the executive of the series. And Malcolm Campbell, I believe, had a hand in suggesting that I be considered. Outline, here's the claim. It uses 6 kinds of surface edges. And I'm going to show you that those principles were evident in cave art. That is, they were discovered by cave artists. I am going then to suggest to you that when we perceive, we look out from a vantage point, but in addition, we, in touch, reach out from this central vantage point. Things lie around us in certain directions, and we can find that out by touching them, or we can find it out by looking. And that's the basis of perspective. And then if you show the environment realistically in a picture, people recognize it. They recognize it in Toronto, and they recognize it in Papua New Guinea. People who've never had pictures in their lives before, you show them outline drawings of people and trees and houses, and they recognize them. Those are realistic pictures. But in addition, a picture is a means of communication, so you can do an unrealistic picture, and if you do it the right way, you end up with a metaphor. You see that sort of thing in a cartoon or caricature in a picture in a newspaper, where some politician is drawn and he's given a long nose that seems to be made of wood because there's little twigs coming out of it. And this clearly then is a reference to Pinocchio. And the suggestion is that the politician isn't entirely honest. Okay, along the way, I'm going to tell you that there are 8 ways to structure visual input. Very few people know that. We don't write that in the textbooks. It's only become really clear to people recently. And when we see movies, it only uses a set of these possibilities. That is, not all the possibilities have ever been made anywhere. The possibilities are logically obvious, but in fact, it's only become obvious recently. And many of the opportunities to make displays have not yet been exploited. I will also tell you that we need a new theory of form. That's Gestalt in German, the perception of form, and I will provide a new theory. So if you're in neuropsychology, then you'll find a little mechanism that I will offer is relatively new and useful. And I'm going to tell you about studies by graduate students, notably Marta Wojnowska, who's working with me and with Matthias, and also some things by Esref Armagan. And Esref Armagan has now written 95 pages of the 4th draft of his thesis, and isn't here today because he's under pressure. So I am not the only person to find out that blind people can draw. If that was true, I would worry, because it might be that I'm influencing my subjects in ways that I don't know. That's the problem in psychology, that often the investigator can interfere in what's going on in perceptual or cognitive processes and influence all sorts of things. This is known as the clever Hans problem. Hans looked very clever, but he only looked clever when he was being tested by one particular trainer. Right? So it was the trainer, not Hans, who was really clever. So this is what I've got here that you make pictures for the blind with. This is a rubberized board with a stiff backing. And if you take an ordinary ballpoint pen, which I found 5 minutes ago, and you do like this, you drag it across the surface, you get a raised line. Now, I do work in art history and psychology and linguistics and to a certain extent in philosophy, but I don't work in physics and chemistry. So the fact that I put the pressure down and the line comes up is some physical, chemical mystery that I regard as a miracle. So I'm going to pass this around, and you can try it for yourself. Feel the lines, the really strong ones I've drawn, light ones that other people tried, and try to make a line too, so you see how it works. So luckily, I'm not the only person who discovers day in and day out that blind people can draw. These are collected by Heike Hammond at the Gemälde Gallery in Berlin. And she has a little program where blind people who are interested in art can come, and she will ask them to do things. So she asked this man, blind man, to draw heads. And he's been blind for a long time, most of his life, and he has done very little drawing, if any, she says Heike Hammond. But it's really clear that this is a good, strong profile. And this is a very interesting, effective drawing of a full face, a front face, face-front person. This is a sort of cubist. This is, well, I'm not quite sure what style. It's sort of a Roman-looking profile, and a very clear one. And this one is by a blind woman, and these dotted line drawings, because she was using her ballpoint pen a little differently than the man, and it comes out more dotted. And these are two people lying down. It looks like a Matisse, I think you'll find. If it's a little obscure, is there any way, Ken, we can turn the lights down? I think they might be behind you, and then it'll be, perhaps that would be helpful. And this is a person lying down, another person, it's Matisse. Now, this is an art class, so of course there should be nudes in the art class for people to draw. Sighted people look at them and draw them. Blind people feel them and draw them. So this is a life class for a blind person. Very nice. And then Tracy from Toronto, that I abbreviate to TT in publications, and I asked her to draw, well, you can tell. What's the top drawing? Bug, insect. What's this drawing? Dog, and this person, right? Man standing facing you, right? Now notice, that's an insect from above, dog from the side, person from in front. So, the basis of perspective is evident there already. That you can choose a direction from which to draw. And notice too, you're not drawing a view or a visual impression. You're just drawing the parts of the object as they are distributed with respect to some vantage point. That's all. It's not that they're drawing visual impressions. I get questions on the email sometime from and people are asking me, how do they draw what things look like? Well, they're not drawing what things look like. They're drawing the shapes of the object, and that's what we see, and so we say that's what it looks like, but it's also what it feels like, because that is its shape. Okay, now I've got a couple of terms here. Line is showing edges of surfaces in these drawings. So what is a surface? I said this for ages in my class, and then one very smart UTSC undergraduate said, he never defines his terms. I thought they were obvious enough, and I didn't need to. And then I realized, no, it's not that obvious. What is a surface? Well, I suggest to you it's a polarized continuous plane. So this is continuous, it's a plane, and it's polarized, it's different on the two sides. It has two slants at any point, orthogonal, at right angles to one another. What's an edge? Well, it's a continuous polarized limit to a surface. So it's different on that side and that's a surface edge. Surfaces and edges are visible and perfectly tangible. I just felt the edge of the table. And I suggest to you, outline shows edges, and we need a history of this discovery started about 50,000 years ago. So what do we get when we come to the history of discussion of these ideas? Well, Edgar Rubin in Denmark said when you have a line or a border, it can show foreground and background. And then it became an unfortunate formula because for decades people said line must show foreground on one side and background on the other. He called it in Danish figur og grund, figure and ground. And people said that must happen. And they're still saying it today. Well, it's just false. It was a misunderstanding of Rabin, as I'll show you. I'm going to suggest line shows foreground surface edges, and there are at least 6 varieties to consider. Furthermore, Wertheimer in Berlin said that when you have dotted lines, like my Matisse drawing of the seated figures from the woman in Berlin, well, if you get the dots, they seem to group as continuous lines, and they're showing the continuous edges of surfaces, continuous edges of tables, or the continuous edges of limbs of people. That's what they're doing. He said that, but he never gave a mechanism. We need a mechanism, so I will attempt to show you a useful mechanism. It's very useful because it shows what the problem is we need to solve. My simple mechanism shows the problem more than it actually solves the problem. So the 6 possibilities. Here we go. Right there is a line standing for background on one side, background on the other, and the line itself shows the foreground surface. Right here we have a background, an empty background, and a foreground surface. That's what Rabin called figur og grund. Down here we have a foreground surface and another background surface, 2 surfaces. Whereas here we only had 1, and here we had 2 backgrounds. Down here we have a very curious case. This surface ends, but the other surface that meets it at a corner continues underneath. That is, you have the impression I could lift the block and the surface would continue underneath. Over here we have 2 surfaces meeting again, but now both of them end, and the line shows a little space or crack. The background is in somewhere in the middle of the line. And here, 2 surfaces end, and there is a line there showing the termination of the 2 surfaces. But there is no crack, and there is no sort of line of toothpaste along there. So no ribbon of material. This shows where they end, and where they end has no thickness, but a line has to have some thickness. So the line is a little confusing here, but nevertheless it works perfectly well in perception. But there's one possibility that you cannot show out of all of these possibilities of foregrounds and backgrounds, of continuing surfaces and ending surfaces. There's one thing that is impossible, and it's in the nature of existence, that you cannot have background, background, and background. That's the one possibility you can't do it. You need a leader to have a follower. You need a foreground to have a background. So that's impossible. Okay, cave art uses outline. The earliest stuff is that we know of, is from Australia. It was found in 2010. So there's very ancient from Chauvet cave in France. What did they show with lines? Well, here is a bird shown 40,000 years ago in Australia. And you notice down here, there is a line. It's a bit like that goalpost line. It stands for the object, and it has background on both sides. Whereas up here, we have foreground, the bird, and then this is empty background here. We go to Chauvet, we have again foreground and background, empty background. Over here, a tail, so we have background, foreground, background. Here we have a mouth, so that is foreground the lip, foreground the other lip, and the little crack in between is the background. So cave artists seem to have discovered all the principles to make all this you need to do with lines and outline drawings. What about dotted lines? Well, they group and they suggest a continuous surface edge, even though there's lots of spaces between the dots. You don't see just a part of the person, and then another part of the person, and then another. No, you see a dotted line standing for, even in the spaces in between, standing for a continuous edge of a surface. How is that done? How are they equivalent to continuous surface edges? Now, you might think what happens is the little dots go in, and then something in the brain strings them together, like a necklace. And because there is a continuous necklace, the thread, that's why you see continuity in perception. But perception is more mysterious than that. You cannot create a model in the brain and then say, that's the basis for perception, because that actually ends up as an infinite regress, because something has to look at the model. Or here's a simpler example. If you took that theory seriously, that you have to copy the thing in the brain if you're going to see it in the world, that would mean for me to see something green, my neuron has to turn green. And it can't do that. No way. So the seeing of color is not dependent upon the neurons adopting the properties. Similarly, the property of continuity is not done by the neurons adopting the properties. We need something else. Let me convince you that blind people can draw with dotted lines easily. So I asked this man, Esref, who has no eyes and never had, born without eyes. He likes drawing. He lives in Ankara. I asked him to draw a flower with continuous lines and with dotted lines, and he did it just like that. I thought it was a fair question because I knew as a child he used to draw on cardboard with a nail, and he would sort of make indentations in the cardboard, dotted indentations. And so he did this spontaneously, readily. Oops, let's go back. So here we have continuous line, and here we have dotted line, and it's fluid and easy, and he just produces them instantly without stopping and thinking about it, as far as I could see. So they're equivalent. Now here is one way we can think about this, and it will make some sense. That solid line, dotted line, and continuous surface edges must be equivalent because they trigger a common mechanism somewhere. What is it that they all trigger? Well, how many people here are in neuroscience? Put your hands up. 1, 2, 3, 4. Not that many, so 5. I'm going to explain this in simple terms then, and perhaps people may challenge me later. What we have on our retina is regions, like circular regions. And sometimes a circular region full of receptors on our retina has a little center to it, and that's called a center surround region or field in the retina. And that center surround set of receptors, all of them, all feed to some cell deep in the visual system, a couple of steps in. Now, if you get uniform light on the center and surround, then they send both stimulation and inhibition, and the central cell just fires at its resting rate. But if the light on center and surround is uneven, that is, if it's unbalanced, then this little cell fires like crazy because the center is sending more stimulation, or the surround is sending too much more stimulation, and it's just unbalanced. The amount of light on center and surround is unbalanced. That triggers the cell deep on. So, dun, 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 I know it looks horrible, but let's go through it a little bit. So, if you had a dot in the center of one of these things, then it would help, it would send stimulation down to some central cell. And if you had 2 of them, they're firing 2 of these more central cells. I've called them C minus and C minus because I want to have one more cell still deeper, C plus. If you have 2 of these firing, that will fire C plus. So this one getting unbalanced light triggers that one. This one getting unbalanced light triggers that one. These firing both at the same time trigger this guy. He needs 2 cells to fire. 2 of the C minuses. That means we now have something that's detecting pairs of dots. And we can do trios of dots and quadruples of dots any time. We can build this up in principle. But notice, if we say that, then we have built a mechanism that will also be triggered by a continuous line. Because the continuous line might pretty much fill the center and leave a lot of the surround exposed. So it's unbalanced. And so that would also fire C plus. So only one more thing we need to do, and that is to get a continuous surface edge to fire C+ as well, and this is how we do it. Say, look, there's a continuous surface edge, and it's only firing, it's only firing a part of the surround, so it's leaving all of the center and a lot of the rest of the surround exposed, but it's unbalanced because this gets nothing and the surround gets some. That gets the center completely exposed and the surround is getting some stimulation. So it's unbalanced. So we can trigger C+ in 3 different ways. Dots, continuous line, and continuous surface edge. QED, quadrat demonstrandum. We have found a mechanism that will do what we need. It will show that dots, lines, and continuous surface edges all do the same thing in the neural system. And I think what happened was when Darwin was evolving us, he put a little mechanism like that in our heads. And then what happened was the cave artists discovered it. Where did they discover? Probably in the Drakensberg Mountains of South Africa. There's very ancient stuff there. There's almost a continuous record up until about 200 years ago. They probably discovered it. And then when people left Africa, they carried this with them. And almost all tribes kept it going. And then the occasional one lost it. And luckily, we have occasionally found tribes who never make pictures, like the Songhay of Papua New Guinea. And when I showed them pictures, actually I didn't, I drew the pictures, and then my colleague, Abe Ross, showed that he lived with them for a year. He would show them the pictures, and the kids and the adults, whether they'd been in the village all their lives or left a lot, they all recognized the pictures at the same rate. So it seems to be a universal. Now, Peter Coffin, graduate student last year, challenged me and said, okay, John, if a set of a few dots is equivalent to a continuous edge, why does a continuous surface edge or line not suggest a few dots? Why is it asymmetric? Oops. So we need another angle on this theory. So here's the possibility. What's happening is, whoops, the dots are triggering a continuous function. You know, if you've got a set of dots on a graph, you look at it and you say, oh, that's linear. And you realize, what's the function that fits in between? And if anybody asked you, what's in between those 2 dots? You could tell them, right? Because the continuous function tells you. But notice the continuous function does not tell you that it is founded on a particular set of dots. It's asymmetric. And of course, if the dots are going like this, accelerating up, then you say, oh, that's the exponent is larger than 1. That's y equals ax to the 4th here, plus b. And so what's going on is that Darwin put in a function system. So you can trigger functions in the brain, mathematical functions, and therefore things that are not continuous can trigger functions which are continuous, and that's why dots can suggest continuous surface edges. And that's the answer, I think, to Peter's problem. Now, those functions are shapes. Shapes are very valuable. Until 50,000 years ago, if a giraffe was coming in, the pattern of a giraffe was coming in your eye, there was a giraffe in the neighborhood. Then we started making pictures, and we started violating all those laws. Now you can get giraffes coming in, and there's no giraffe, just a picture of a giraffe. But of course, our brain was evolved during the times when the information in shapes was absolutely 100% reliable, or let's say 99.9999%. Giraffe coming in, there's a giraffe. I mean, nobody ever cuts a rock and finds a perfect picture of a giraffe inside it. Nobody ever looks at the sand as the sea goes in and out and says, my God, look, a perfect picture of a giraffe. There are almost no illusions in nature. If you ever find an illusion in nature, people will drive for hundreds of miles to see it. You know, they do this in Nova Scotia or somewhere where there is magnetic hill. You park here, take the brake off, and your car seems to drift uphill because everything's at a funny little slant, right? And you get fooled about where the horizontal is. That's an unusual thing in nature. There are very few pubs that contain illusions when you're sober. But there is one, and it's called Smokeless Joe's, and it's on John Street, opposite, it's on the east side, opposite the cinemas. And if you ask them, the barkeeps will take a marble and set it on the back counter and step back, and you will see this marble roll uphill. Because what they did was they took all the tiles and tilted them very slightly, right? But that's very unusual, very unusual. Perception evolved to pick up highly informative patterns that tell you about objects in the environment. That's called specificity. So, summary. Lines show surface edges. Dotted and solid lines trigger C+ cells. The result is grouping and continuity. There is a common mechanism with surfaces, hence things can represent surfaces. Now, a little extra here is, we actually have 8 ways you can structure the light coming in your eye. You can have pure color pictures or black and white pictures. And of course, black and white pictures is very common. We make movies that are black and white. One's just won an Oscar. You can also have purely monocular pictures, and most of the pictures that we see in the movies are monocular. Close one eye, still looks perfectly good. There are very few pictures, but they're becoming very popular, and that are like Avatar, where you need binocular vision, right? Then you can also have pictures that when they're static, you can see them, all the structure. There are others which we can cleverly design with animation. So everything has to move before you can see any edges. Right? You can get a picture that if you just look at one part of the movie, just one frame, just looks like wallpaper. Next one just looks like wallpaper. But you sequence them, and what you see is, say, a leaping dolphin. Leaping dolphin is only there across the set of pictures. Now that produces 2 by 2 by 2, which is 8. And only some of the 8 has yet been exploited. My hypothesis, as yet untested, because we haven't yet made all the things we need to test it, is that outline works the same way in every single one of those domains. So I'm telling you about where we are at the moment, but it is clear there is more to do. Second part, perspective. I've talked to blind people and said, you know, I'm working in perspective, and they say, what's perspective? I'll never understand that. Oh, that's so complicated. And I say, well, imagine you are standing in a big road, and there's 2 trees on either side of the road. Point to them. And they do. I say, 2 more trees, 10 meters down the road. Where are they? Point them. Next, 2 more trees. Point to them. 2 more trees, 2 more trees, 2 more trees. I said, see the way your arms are coming together? That's perspective. And the blind man said, oh, is that perspective? I've always understood that. So, let's see how it works. Perspective. Here's what happens. There's a set of steps. They're all the same distance apart in the ground, but the angle made at the vantage point keeps shrinking. So sometimes it's 21 and sometimes it's 5 degrees. And the shrinkage is at a very fixed geometric rate. Now, there's also the width. So that was the steps between. The width of a tile projects smaller and smaller angles as it goes further and further away from you. This is called azimuth, the width. This is called elevation, the way things are rising as they recede from you, rising towards the horizon. So, as a result, if you draw a perfect perspective picture, what happens is the things near you have a certain angle in your picture, and the ones further away make smaller angles. But in addition, the width doesn't shrink as fast as the elevation. The width shrinks at an approximately linear rate when things recede, and the elevation shrinks at an approximately quadratic rate when it recedes, a faster rate. That's why here it will look a bit like a square, and over there it looks sort of like a brick. And we actually slightly underestimate the rate of change. So we often make mistakes about angles and sizes in the distance. Small mistakes, but nevertheless mistakes. And the guy who worked this out with me was a graduate student, Igor Yurichevich. Now, of course, it's been out for a couple of years, so we doubt all kinds of things about it, and Marta is supposed to fix up this theory with Matthias's help. So the elevation-azimuth ratio tells you about depth. That's the information for depth. Therefore, a whole line of philosophy started by Bishop Berkeley is wrong. He said in 1709, distance is a line directed endwise to the eye. It projects only one point, and therefore you can't see distance. You must get your information for distance from somewhere else. He thought you got it out of touch, and that's just wrong. Contra Kant as well, 1781, space is not an experience which can be derived from outward. Whereas, of course, the argument here is, no, there are certain very distinctive patterns called perspective ratios that tell you about the distance of things. And Helmholtz said, oh, distance is actually an inference. You can't actually see it directly. There's no direct information from it. Well, that's just simply wrong. And Goodman, philosopher, major philosopher, Harvard University, one of the major philosophers of several decades of the 20th century, said perspective is just a convention. Well, it's wrong. Perspective is something that vision uses, and I think it's used by people throughout the world, and it's used by children and adults, and it's used by the blind. So I think all these guys have the disadvantage of being wrong. The advantage of being interesting and fun to attack. So here we go. Here's a drawing by TT of a house. Now notice there's a rectangle for the front of the house, but the roof, which is still a rectangle, is shown by lines converging, as like in Juricevich's pattern of tiles receding to the horizon. That's converging. It's converging in only one direction. That's called one-point perspective. This is the end wall of the house, and then you get the pitched roof evidently shown nicely. But over here, this is the roof from above. Notice now both rectangles converge. This converges up, and that converges down. That's called two-point perspective, because you're converging in two directions in space that are orthogonal to each other. Now, space only has three directions, right? That's all it's got. So if you can draw, using convergence, in all three directions, you can draw everything that can exist. So can anybody do that? Well, most sighted people have trouble, but they do master some parts of the system. There is, I think, a developmental trajectory that leads us to using some perspective. And by hypothesis, the blind have the same trajectory. So, in touch as well as vision, do we appreciate the angles made by objects in elevation and azimuth as objects recede? Well, thank you, Marta. Let's have a good look. Here's what Marta did. She put little dots on the ground, built an apparatus, put people in the apparatus there, and they had to point to the targets. There they are, the targets on the ground. And she would then test them sideways, azimuth, and also test them in elevation. She would let them feel the things with a rod or look at them. She tested blind people as well as sighted people blindfolded or not. And what was the result? Well, here we go. Here are people blindfolded after viewing. There's their data, there's their azimuth when they're close. And notice as the objects recede, the azimuth decreases. This dotted line shows what it would be if they were pointing from their shoulder. But they may be pointing from here or here. We don't know. We just said, okay, we'll track it from the shoulder, but we'll see, in principle, do they decrease at a suitable rate. So that was the blindfolded. Blindfolded after touching the things and then walking back to the apparatus, and they're also decreasing. And now what about the blind? There they are, the blind. Oh, identical to one of the sighted. Oh, now again. Now in between two of the sighted, and now identical to one of the sighted. So statistically, they're no different than the sighted on average. That's one direction. That's azimuth. Now let's try elevation. So what have we got? We've got the blind and the sighted and the blindfolded sighted all there, just really close all along. Their elevation system seems to be terrific. I mean, they're identical, the blind and the sighted, tested various ways. The measurement from the shoulder is actually close there and a bit off here, but it may not be the shoulder that they're using. That was just a guess. So what can we conclude? That after viewing the circles or touching them, blind or blindfolded, they're the same. They all understand the way things shrink in the distance. They all understand perspective. Now, understanding it isn't quite the same as using it in drawing. So let's see that. Will they use it in drawing? So here's a drawing by Esref. It's a set of glasses, 2 sets of 3 glasses receding across the table. I mean, this is terrific. I'm going to concentrate on individuals, but I have done this work with groups of blind people, and similar things occur. Notice this glass has a very rounded top, and that one is a more elliptical top. This is large, that's small. This is hidden or occluded by this one, partly. Same thing occurs over here. Big circle, more elliptical, narrower spaces in azimuth. And this is lower in the picture plane, and that's higher. This is really quite a good little perspective, freehand drawing. It's really very good. It's impressive. Okay. And by the way, Esref is now in a movie made in Berlin, and it's about an hour and a half, and it's called, in English, One Who Sees with His Fingers. Got a sexier title in German, I'm sure. And it's just released this year on DVD. Okay. Then I asked him for a cube, then a cube balanced on a point, cube moved to the side, cube moved to the side and down. I mean, this is really excellent use of the vantage point. And there are relatively few sighted people who can draw a cube balanced on a point as well as this. I was writing this all up, and I said, that's 90 degrees, that's 90 degrees, that's 90, that's 90, that's terrific. And then I thought, oops, I better measure this, because I've often noticed errors in people's writing about pictures and drawing when you come to measure them. So I measured them, and that angle is different than that angle. That's obtuse and that's acute. The difference is about 20 degrees. So Sharif has now been doing a PhD on that illusion, and he can find people making errors of as much as 40 degrees in doing this kind of task. It's just huge. Mammoth errors when people try to read the shapes of features on picture surfaces. Take away all of these other lines and just give them the rectangle, and then they're basically 100% correct. As soon as you put the information for depth around, huge errors emerge. The first time this illusion could have been made was 40,000 years ago. This is a creature of pictures being made. So perception is just about 99.9% accurate till about 50,000 years ago. And then we discover not only how to make pictures, but how to make illusions. This is when illusions become common. So we tried this with long lines, tried it with short lines. Turned out it was exactly the same strength of illusion with big lines and short lines. So it has to do, we think, with the apparent tilt of that top surface. We tried it with very irregular figures, and it turns out it was exactly the same illusion and strength. So it looks like it's the information for tilt around here, not directly to do with familiarity or length of lines or convergence. It's even strong with parallel perspective, which contains key features to do with tilt, which are this Y junction and this L or little L junction up there, and the asymmetry or eccentricity of this shape, we think. Turns out when you stick in a few other junctions, little X's, forming a nice gradient or texture, the illusion gets stronger. It also gets stronger if you make the cube tilt. And so Sharif has done just a host of little experiments showing this illusion cutting across many conditions. And the general theory is, he has another one where you can't, That one you can't see. If you make the texture of the surface be like lined paper, then the illusion decreases. That is, it becomes easier to read what's on the surface. If you remove as much of the apparent surface as possible by making the lines white and the background black, for example, then the illusion gets stronger. So the more it looks like the pictured scene, the stronger the illusion. The more it looks like you're looking at a surface, the weaker the illusion. We can strengthen it and weaken it appropriately, following this kind of theory. That what's going on, invented 40,000 years ago, is that there is two kinds of information at once: information for the pictured scene and information for the picture itself as a surface. And the two interfere with each other. The first time there was ever an opportunity to have that was 40,000 years ago. Now, I asked Sharif to draw a house, and he drew, first of all, this one, which is largely parallel lines for the house. And then he said, there's a better way to do this. He himself said that. He seemed to just invent it right in front of me. And he said, I'm going to make those two converge. Or he used the words narrow. That's what the translator said. And I'm going to make this one narrow. That's his word. It's translated by Joan Ehrencel. And so he's shown two-point perspective right there. Can he do three-point perspective? Thought that would be a nice challenge. This is what three-point perspective is, and most sighted people don't understand it. Why? Well, this one, back. This one looks right for most sighted people. That one looks twisted, and that one looks thin and twisted. But it turns out they're all drawn in perfect perspective. And they found this out in the Italian Renaissance about 1413. Brunelleschi invents perspective. And so the contribution of Leonardo da Vinci to the study of perception and perspective is to say, only show these. Don't show those, because they look wrong. And the bishop won't buy them. And you won't eat. You want to become rich? Show these. So Kodak makes cameras and decides, I'll go for narrow angle lenses. So you take a picture and it all looks realistic. But if you take a wide angle lens, then you get all these things here and they look distorted. And so people start to say things like, oh, perspective is a convention. It was invented. It isn't something the eye really uses. A lot of confusion arises about this. But let me just say for the moment, this is correct. And to give you an idea, an intuition of it being correct, I want you to think of Spider-Man swinging over the Empire State Building, and he's got his camera and he takes a picture for the Daily Bugle, and of course you see the Empire State Building going right down like this. But that also means any buildings beside it are also converging down in direction. So the roof is converging in a couple of different directions, but also everything is converging down, and anything on the side in his picture must lean in like that. Now, most sighted people don't know that and can't draw it. But I asked Esref to draw 3 cubes, one in front, one to the left, one to the side. He stopped for a moment, put his hands like that in front of his face, and then drew. I said to him, Esref, can you tell me what you're thinking and as you draw? And he said, John, I can think or I can draw, but I can't do both. So he couldn't explain what he was doing, but he did it nonetheless. There we go. So this is converging up, and those are converging in the same direction. This is slightly converging down, that line suggests, and that is definitely converging in that direction and leaning in that direction, and they converge in size to the left. So it's converging in 3 directions. So he can do 3-point perspective. I think he invented it doing that drawing right in front of me. So I said to Discovery Channel, would you like to take us to Florence and have Esref sitting at the baptistry where perspective was invented? And they said, okay. So they took us here, sat us down here, looked at the building. Now notice these 2 sides converge at 45 degrees, so they're going to converge top and bottom. And the front remain roughly parallel, but you will notice it converges slightly upwards because of the way I took the picture. So we sat Esref, I let him feel the corners of the building, took him back, gave him a model of the building, and said, I'm holding the little model right there. And I said, Esref, could you draw this? And Discovery Channel was taking pictures. And so he drew things. I will show you one of his drawings. There it is. It's really very good. And notice he's converging those two 45-degree sides. I show this drawing to sighted people in my classes, and I say, could you draw this? And they look at it, okay. I put it down, and then they try to draw it, and almost always they can't do it. There's a developmental progression in the ability to get the perspective intuitions out onto the page. If you draw a lot, you'll come close to this. Most sighted people need to be told that final step, and he actually worked it out. And I saw some of his working out drawings, including this one, which is the one that appears mostly in the Discovery Channel documentary. I got about 8 drawings, and of course they only show one. And you'll notice it's probably converging up, and it's certainly converging left and right. And then he adds a couple of extra sides that don't belong, probably just because he's working out the principles. Very smart. So, perspective. We do it. We use it all the time. We understand it in pointing and reaching and doing all kinds of looking outs. And then it can be used in pictures. Well, what happens if you now try to violate realism? You get metaphor. For a message, you can violate the pictures. So let's see what people do. Here's a sighted person, 1810. This is the first time that this occurs. This person draws motion by adding little circles inside the wheel and making the spokes fade. First time, 1810. First time in the history of art. And as soon as this guy invents this way of violating the rules, it spreads like wildfire around the world. As everybody says, oh, that's a good idea. And you get things like this. There are not multiple hammers. There is only one hammer in motion. The bell is not shedding parts of its outer skin. It's just vibrating. And behind this funny little spaceship, these little lines are suggesting some sort of motion. I've actually seen drawings like that in the Eagle comic in Britain for the Black Cat space vehicle. Ta-da! So I drew that one. Okay, now let's look at Eriko. Eriko is blind, has been blind from early on in life. She's now in her early 30s. That she starts drawing. She came here, made drawings here. I have her very first drawing ever. Her drawings were encouraged by Elke Zolich, who's just a grade school teacher. I met her in Berlin and said, I have blind children in my class, and they like to draw. Why don't you try drawing? So she said, okay, I will. Here's a drawing from Mexico. So Eriko goes to Mexico and takes her little drawing kit with her. Ha ha. For the first time in the history of the world, a blind person takes a drawing kit with her and comes back from her voyages, my impressions of, in this case, Mexico. And so it's clear, it's clear that this is a glass, right? And straws, and there's levels of liquid in there. And then she says, it's not just water, liquid, this is tequila. So this is the effect of tequila. And this, you know, you're sitting at the table, you're there with your lover, Michael, a wonderful man, and the mariachi band appears from nowhere and circles your table and blasts, and there is a trumpet in the band. Whoops, there's a trumpet in the band. No, there's a trumpet, starts there. This is a way of showing, symbolizing, a metaphoric shape for the trumpet. Starts in one place and fills the space at the top. You look in there and you see curved lines. That's the violin playing. And if you look carefully, you'll see little zigzag lines, castellated lines. That's the guitar, clink, clink, clink. And here, there's some rhythm instruments, so there's lots of horizontal lines. And then she goes swimming off Isla de las Mujeres in the sea, and it's wonderful. Oh. And so she expresses this by drawing herself swimming in the water. There's the water. And you can see the back of her swimming costume. There's her head, there's her hair. But there's all these webs of lines coming from her fingers and toes. And she said, that's the feeling of the water streaming through your fingers. And then she said, you know, that might be metaphoric for the sighted, but it's perfectly literal for the blind. I interpret that to mean you can feel the edges of a stream of water that you can't see. And she was quite right, very insightful. And then she's in Germany with Michael. They're living in Augsburg. She needs to get a job. She's blind, needs a job. She was trained as a librarian in Canada. She needs a job as a librarian in Augsburg, a small town. She's having trouble landing a job. So she sits on her balcony and she takes her cup of coffee. She wants to make friends. She wants a job. She has problems. She drinks her coffee. There's the heat and steam coming to her hand. And she thinks about her problems. And these curved lines are her thoughts going round and never coming to an end. Never solving her problems. And there are zigzag lines, because every now and then she sighed. The afternoon, the wind. She's sitting on the balcony thinking about her problems. I think this is brilliant. And it's on exhibit with another set of her pictures at Joshua Creek Exhibition Centre, Heritage Art Centre, which is 403 and 407 Oakville, Burnhamthorpe Road. I'm going to give a talk 2:30 on Sunday. And if you'd like to come, you'll see lots of her pictures, and I'll talk more about her. There'll be a little concert, my talk, and a reception. So, where's her influences? It's hard to tell. Futurist, expressionist, not sure. There's Errico, there's Michael, they're not married. No, Diderot, some years ago. Diderot, 1713, 1784, brilliant French intellectual, the encyclopedist. He invents the encyclopedia idea, among other things. Goes to jail for his ideas, free thinker, wonderful man. He observed the blind man from Puiso. People drew profiles on his hand, and he recognized them. He observed that and wrote about it. Now, he could have had everything that I've told you here, almost all of which is common sense. There's a line standing for a profile, which is a surface edge. He could have said that, and then asked himself, oh, what else can a line stand for if it stands for surface edges? And he could have written it down by, the answer, by sitting there for 10 minutes and writing out the answer and making a few drawings. A profile is something from the side, so perspective is relevant. He could have said that, and then say, oh, no, what's going on in perspective? And most of what I told you is common sense. I mean, blind people understand this thing about trees and distances intuitively. He could have said all of that. He could probably have said then, well, if they're realistic, can they ever do non-realistic things, and why would they do that? I think he made the key observation, and it sat there for hundreds of years until today. And now it's in the last few decades that we're discovering, that we're thinking about the relevant observations that are relatively easy to interpret. So, my conclusions are, they're controversial in some parts of the world. Lines show surface edges in vision and touch, and there are 6 types at least. Perspective is in vision and touch. Part 3, pictures for the sighted and the blind can be metaphoric. Quite a number of students have influenced me over the last couple of years, and many before that. Sharif Ahmed, Marta, Justin from UTSC, an undergraduate, Heba from UTSC, Marcelo's from Brazil, Sinyi Chao from Taiwan, and Peter Coffin, who asked me that wonderful question about why is it asymmetric? All of these guys have pushed me and taught me many things, and I just love talking about this stuff. Thank you for listening.